Hi everyone, my name is Claudia Prieto from King's College London, and I would like to thank the organizers of the 2020 SMRI meeting for the opportunity to talk to you about advances in cardiac imaging. Cardiac MRI enables comprehensive assessment of cardiovascular disease, providing anatomical, functional, and tissue characterization information, including coronary MR angiography, myocardial perfusion, as well as qualitative and quantitative myocardial tissue characterization such as LG imaging and parametric maps. Conventionally, cardiac MR protocols consist in the sequential acquisition of multiple contrast and quantitative maps, most of them performed in 2D with different orientations and under multiple breath-holds. However, this leads to long scan time of about an hour and requires about 40 breath-holds per scan session. So a common goal of several groups in the community has been to enable fast, efficient, easy to plan, and patient-friendly protocols to acquire all this multi-contrast and multi-parametric information in a few scans, ideally with all of them performed under free breathing and in 3D, resulting in considerably reduced scan time while still providing all the information required for comprehensive assessment of the disease. During the last year, several methods have been proposed to move towards these goals. These include those approaches that aim to provide simultaneous multi-contrast or multi-parametric information from a single scan, such as MR fingerprinting, multitasking, as well as block simulation-based steady-state approaches, which need to be complemented or combined with solutions that exploit the high-dimensional motion directions to resolve or correct for the cardiac and respiratory motion that happens during the scan. These multiparametric and motion-related approaches rely on highly undersampled acquisitions. Therefore, powerful reconstruction algorithms are needed to fully exploit the redundancies in the data, leading to several developments in the areas of deep learning physics-informed reconstruction, motion compensation, block equation-based dictionary generation and matching, among many others. Although extremely interesting, it is not possible to cover all these topics in this talk. So I will be only covering the first of these, focusing on parametric mapping for myocardial tissue characterization with MR fingerprinting. So conventional mapping techniques acquire a series of weighted images at different points along the T1 or T2 relaxation curve. And this is achieved, for example, for T1 mapping by acquiring data with varying time delays after an inversion or a saturation pulse. The series of weighted images are then reconstructed and fit to the exponential model of relaxation in a pixel-by-pixel basis to obtain a single parametric map. These approaches, although very powerful, present several limitations. These include the need to acquire several weighted images that result in long scan time. The simplified exponential models that we use for fitting with these approaches are simple, but also highly sensitive to system imperfections, affecting accuracy and precision of the techniques and leading to maps that are system and site dependent. And as mentioned before, these approaches usually provide information of a single parameter at a time, which are performed sequentially and therefore not necessarily co-register. MRF, on the other hand, attempts to capture the continuous transient state of the MR signal evolution to provide multiparametric mapping from a single scan. The first essential component of MRF is a variable pool sequence able to generate unique signal evolutions for each combination of parameters, in this example for T1 and T2. That means that different to conventional mapping approaches, the shape of this signal evolution is not relevant as long as we are able to differentiate between them. Since we know the sequence that is being played, we can generate a dictionary of possible signal evolutions for certain range of the parameters, for example, using block simulations. Now, for each combination of sequence parameters, we acquire a highly undersampled dataset using, for example, spiral or radial trajectories. The important part is that the trajectory is such that introduces incoherent aliasing in the reconstructed time point images to not affect the subsequent dictionary-based matching step. Now we can look at the signal evolution of each pixel in the image or fingerprint and match the acquired signal to the closest entry in the previously generated dictionary. In this case, we're matching the signal in yellow, which allows to retrieve the specific T1 and T2 value associated to that entry in the dictionary. And we can repeat this for all the pixels to generate the T1 and T2 maps. This approach works nicely for static images. However, further modifications were needed to enable cardiac MRF, and these were introduced by Jesse Hamilton and Nicole Seiberlich in 2017. Cardiac MRF uses ECG triggering to minimize cardiac motion, whereas respiratory motion is minimized performing the acquisition and the breath hold. And variable magnetization preparation with interleaf inversion recovery and T2 preparation pulses is employed to increase sensitivity to T1 and T2 parameters. A typical sequence is shown here, enabling simultaneous quantitative myocardial tissue characterization of T1 and T2 in a single scan of 16 seconds. Now, different to conventional MRF, subject-dependent dictionary generation is needed for cardiac MRF to include heart rate variations and ECG stamps. So the group of Nicole Seiberlich has demonstrated the use of cardiac MRF pre- and post-contrast in patients both at 1.5 Tesla and 3 Tesla, showing good agreement with conventional mapping techniques, as we can see here as example for a patient with dilated cardiomyopathy in the first panel, and a patient with transmural scar in the second panel. In collaboration with Nicole Seiberlich, the group of Ruth van Henswijk has shown very interesting results for the use of cardiac MRF in patients with implanted ICDs, as we can see here for 2 patients, where cardiac MRF on the top shows fewer artifacts and higher map quality than conventional MOLI and T2 prepare-based methods that are shown in the bottom. Now, since several recent clinical studies have shown that epicardial, myocardial, and perivascular fat can be associated with different adverse cardiovascular outcomes, in our group, we have extended the cardiac MRF approach to provide further myocardial tissue characterization by enabling simultaneous T1, T2, and fat fraction estimation in a single scan of 15 seconds, allowing at the same time to reduce water-fat partial volume effects in the parametric maps. This is achieved by extending the acquisition to a 3-echo gradient echo encoding with a radial acquisition trajectory, from where water, fat, and V0 images can be obtained using a Dixon-type water-fat separation. We have applied this approach before and after contrast in patients with suspected cardiovascular disease, showing comparable or better image quality than conventional maps, as we can see here on the second panel, with conventional maps shown in the top and Dixon cardiac MRF shown on the bottom. This is also observed here in a patient with a scar for acquisitions both in 2-chamber view and short axis, and the scar was also visible in a synthetically generated LGE image coming from the MRF scan in comparison to the conventional LGE acquisition. Also, there are other solutions to provide water-fat images. For example, this work from the group of Nicole Seiberlich using rosette trajectories, which is also showing very promising results. Now, MRF can also be extended to quantify other parameters of interest, as shown, for example, here for simultaneous T1 and T1 raw myocardial quantification, using spin-lock T1 raw preparation pulses with the aim of providing contrast-free fibrosis assessment. These preliminary results from our group show very good agreement with conventional mapping techniques in phantom studies and feasibility in healthy subjects. Now, the previous approaches are ECG triggered to a short acquisition window of usually 150 to 200 milliseconds to minimize cardiac motion. However, this is highly inefficient and can limit the spatial resolution of the scan. In order to increase the scan efficiency and extend the acquisition window at each heartbeat, we have recently proposed a low-rank motion-compensated reconstruction that estimates motion from the cardiac resolve reconstruction covering about 450 milliseconds of the cardiac cycle, and incorporating this estimated motion in a regularized, dictionary-based, low-rank inversion reconstruction. This approach, shown here in the last column, enables cardiac MRF acquisition with longer acquisition windows, leading to better map quality than conventional MRF with the same scan time, as shown here in the second column. Now, all these methods mentioned before are based on 2D acquisitions, but cardiac MRF can also be extended to 3D, enabling extended coverage of the heart. This is an example from our group where we have used autofocus translation correction based on respiratory velos to estimate and correct for respiratory motion, enabling free breathing 3D T1 and T2 cardiac MRF in about 7 minutes scan time. This approach enables whole ventricle coverage, achieving similar quantification than conventional maps as shown here for several slices of 3D MRF for T1 and T2 map. Now, instead of relying on ECG triggering and correcting for motion during the scan, free breathing non-ECG trigger multi-contrast acquisition can be also performed. One of such approaches is multitasking, which was proposed in 2018 by Anthony Christodoulou and Debbie Oli from the CETA-SINA. The idea of multitasking is to exploit redundancy of the different temporal and contrast direction, recognizing these multiple overlapping dynamics as multiple dimension or task, which can be addressed by using a low-rank tensor image model to capture the correlation between images. After reconstruction, this high-dimensional information can be unfolded to visualize the processes of interest separately, allowing, for example, in this case, to visualize cardiac, respiratory, and T2 prepare IR signal evolution for multi-contrast imaging, allowing to generate Cine T1 and T2 maps. This approach can also be extended to other dynamic processes, as shown here for 3D perfusion, and also to other organs of interest, as nicely shown here, to enable 3D bright, black, and gray blood comprehensive assessment of aortic disease. So in summary, I hope I was able to show you that simultaneous multiparametric assessment and quantitative tissue characterization of cardiovascular MRI is feasible, and that there is still the possibility to extend this method beyond T1 and T2 mapping to other tissue parameters. I believe these approaches have a huge potential to simplify scan planning and reduce scan time, ultimately leading to more efficient scan sessions. Although not discussed here, deep learning-based techniques can help to further accelerate acquisition and reconstruction of these approaches, and of course, clinical validation of this method for different cardiovascular diseases is needed. So with that, I would like to thank those who kindly provided slides for this talk, our team at KCL, and you for listening.